Hi, I'm Professor Angela Rasmussen from the Department of Electrical and Computer Engineering at the University of Utah. Today we're going to go over a Bode plot example. In particular, this was the quiz that you just took. So we're going to start with a transfer function, and we're going to use this to create both the magnitude and the phase plots for this equation. And this equation, remember, is derived from a circuit that contains time-dependent elements such as capacitors and inductors. So that is where that S comes in, is that S is equal to J omega. And so when you transfer an element from the time domain into the frequency, you get an S component in it. So this circuit has already been solved. We have a transfer function, and now we want to graph this as the Bode plots from the magnitude and the phase. So the first step in doing that is that we need to get the correct standard form. And so we're going to manipulate this to change it to standard form. So that means we need to get the S quantities to be an S quantity plus 1. So that means we need to move this out and this out of the equation. And so in order to do that, we need to multiply this bottom part by that 1,000. And that will leave a 1. And then here we have 2 of these because of the squared. So we're going to have S over 10 plus 1 squared. And you can go back mathematically and confirm that this is the same exact equation. We're just manipulating it into this form. So multiplying, I forgot to bring this. This is multiplied by 1,000 in order to make that quantity the same. So 1,000 times 10,000 divided by the 10 times 10 gives us 100,000. And then 10 times 1,000 is going to leave us with 10,000 plus 1. And on the bottom we'll have S over 10 plus 1 squared. So if we go back and look at these equations, you can see that it's not the first equation and it's not the second equation, and so it looks like it is the same as the third equation here. So this would have been the correct answer, is to have equation 3, and you can see the difference also in equation 4. So equation 3 was the correct one to obtain this as a standard form. So I'm going to copy this, and now we're going to look at graphing it. So the standard form looks like this, and we want to first identify the poles and zeros here. So remember that the zeros are the quantities that are in the numerator. So we have a 0. I don't know if I said that right. The zeros are the numerator and the poles are in the denominator. So a 0 at 10,000. And then because of the squared, we have 2 poles at 10. And remember that this unit for any of the omegas here is radians per second. So now when we go to graph this, we're going to graph, this will be our magnitude Bode plot. And for the magnitude Bode plot, we are going to have dB as the y-axis, and then we're going to have, for the x-axis, it's going to be radians per second. Now once we get this into standard form, we notice that we do not have poles and zeros at the origin. So we are going to have a flat line till the very first polar 0, which will be at 10. And we're going to have 2 poles at 10. And then we're going to have a change again at 10,000. So we need to find what that magnitude is at 0, or at before 10 radians per second. And so all we need to do is take 20 log of the coefficient out here. So 20 log, again base 10, remember, of 100,000 is going to be our starting value, and that's 100 dB. So we're going to start the magnitude at 100 dB. And then it's going to be before this value at 100 up to 10, where we're going to see a change of 2 poles. And the changes for poles is going to be a minus 20 dB per decade. But there's 2 of them, so you multiply that by 2. So we are going to have a change at that location of 10 to minus 40 dB per decade. So between 10 and 100, we are going to change by 40 dB. So that means this goes down to 60 dB. And we're going to keep having that 40 dB change until we reach another polar 0. So that's going to keep going down by 40. So from 60 to 40, that goes down to 20. And from 20 minus 40 is going to be a minus 20 dB. And then at 10,000, we are going to have 1 0, and the change for a 0 is plus 20 dB per decade. So with that change, we are going to have from minus 40 to plus 20. We add those together, and that still gives us a minus 20 dB per decade change. So between this decade and this decade, we're going to go down now half of what it was, and then down another half. So from minus 20, this middle will be minus 20 more, so minus 40, and then 20 more will be minus 60 dB. And then that will keep going on at that slope continuously till the end of frequency. For the phase, so this is our magnitude plot. For the phase, this will be our phase plot. Phase has degrees for the units in the y-axis and radians per second for the x-axis still. And we didn't have any poles or zeros at the origin, so we are going to start this at 0 degrees. So our equation again is this, and so we have 0 degrees, and we know that we have changes that are centered around 10 for the phase, and then we have changes that are centered around 10,000. What I mean by centered is that 1 decade before and 1 decade after that is where you have an effect in phase changes. So 1 decade before the 10 and 1 decade after, we have the effect of a pole, which is minus 20 or minus 45 degree slope per decade, but there's 2 of them, so we multiply them by 2 to get minus 90 degree slope change. For the 0, we go 1 decade before to 1 decade after, and that is a plus 45 degree slope per decade. That means decade again is a grouping of 10. So before this change we have 0, but then at 1 we have a minus 90 degree slope change, and that's per decade. So between 1 and 10 we go down by minus 90 degrees. And again we have that minus 90 degrees between 10 and 100. So these changes are minus 90 between 1 decade, and then another 90 to get down to minus 180. There's no change you can see in between 100 and 1000, so that stays flat at minus 180. And now we have an increase of 45 degrees per decade in that range there. And then again, there's no change, so that's going to stay at minus 90 for the rest of this graph. So a couple things I wanted to note here. Actually, before that, we need to go and look at, so these are our graphs. So for the magnitude, you were given options for this graph. So you can see it's not going to be this first one because that starts at 80 dB. This one starts at 100 dB, and we can see that we have a 40 change, and then again a 40 change, and then at 1000 we have a different slope between 1000 and 10,000. And that's not correct either, so that's not going to be the second figure. For the third figure, again we start at 100. We have so this is correct, and then we see that we have a change at 10, and then it goes 40, and that looks like 40 and 40, and then we have a change again here for a different slope. So it looks like figure 3 is correct, and we can just double check figure 4 here. We see that there is a constant minus 40 dB change between each decade, and then that is not going to be correct. So this figure 3 was the correct answer. And for the phase, we're going to go compare the graphs that were given. So for the phase, we see that the first one starts at 0, it goes down by minus 90, but then it's flat the rest of that way. So that doesn't match our graph. Again, this doesn't match our graph for the second figure. That also starts at minus 180, which is incorrect. And for these two, we see we have a minus 90 for this one, and then again a minus 90 to get to 100, and then it goes up from there. So that one's not correct, so it ends up looking exactly like figure 4, and this would have been the correct answer for this one. So a couple other things to note is that this is a hand approximation. So what that means is that at the corner frequencies, or what these are called critical frequencies, where it goes from a flat region and then has a change, each of those changed points is a frequency change. So that would be here. We know that with the hand we do an abrupt change, but realistically that will not be exact. So what it will really look like is a slight curve, and then there'll be another slight curve at the next change here. With this being two pole changes, we are going to have a minus 3 dB change for each pole. So this is going to be a minus 6 dB change from the 100. So actual value here would be 100 minus 6, so 94 dB. And that would be a more accurate number. We also say that this circuit operates up to the point of that first change where it's flat. So this flat region in here is the operating range, and so this circuit operates up to 10 radians per second. And again, we can change that into hertz. Remember, omega is radians per second is equal to 2 pi f. So f would be omega over 2 pi. And that is usually a number that's more familiar to us. So we can convert that if we want. Similar things happen with the phase graph. Instead of having an abrupt change at 0, it's going to have a curve to it, and then it's not going to quite go down as far, and then it's also going to have another curve there. So the actual graph for the phase looks something more like this than the abrupt changes. Those details don't really affect us when we're looking at operating range. And later on, you're going to learn in follow-on classes what the phase change means for stability. And usually you look at the circuit phase change to say, is it stable or not? And you'll get into that in feedback theory. All right, that concludes this example. Thank you for watching.